that for linear sums of sequences, the ROC is the intersection of the ROCs of the individual sequences. The ROC of the sum or the linear weighted sum is the intersection of the ROCs of the individual sequences. So some more ideas. See, Laplace transform is similar to Z transform. So I will have some slides showing you the connection between Laplace transform and Z transform. In the Laplace transform, we have the imaginary axis. We have the S plane because you are calculating x of s using a continuous time integral. And you have the S plane. The S plane is again like you have the imaginary axis, j omega, and you have the real axis. So you have points on the S plane, and the ROC concept is also there in the Laplace transform. So suppose you have the ROC for a causal sequence. So then the ROC will, because it is an intersection. Suppose you have summing two causal sequences. So because you have the intersection of the ROCs of the individual sequences, then the sum of two causal sequences will have an ROC which will extend outwards from the origin-centered circle that lies on the largest finite magnitude pole of x of z. So you have to see like which. Suppose you have two circles and two concentric circles with two different radii, and you have to find out the intersection of the ROCs. So suppose one of them is a smaller circle and another one has a larger radius than the previous one, then the intersection will be the region beyond the maximum magnitude of the pole of x of z. So similarly, for an anti-causal sequence, you will have the intersection ROC which will lie on the smallest non-zero magnitude pole of x of z, and it will extend inwards from that. So these are two ideas of ROCs for linear sums of sequences. If you have linear sum of causal sequences, then the ROC of the sum will be the intersection of the ROCs of the two individual sequences. Therefore, the ROC of the sum will extend from the maximum magnitude pole, and it will go beyond that radius. And similarly, for two anti-causal sequences, you will have the other way around. The intersection ROC will be going inwards from the smallest non-zero magnitude pole of x of z. That is the sum of the two sequences. So that is how we think of linear sum of sequences. For example, let us take a small example here. We want to calculate the bilateral Z transform of a two-sided signal. So it extends on both the positive side and the negative side. So the sum W of n is a signal which extends both on the positive side and the negative side. So suppose x of n is the causal part, 0.9 to the power n u of n, and y of n is the anti-causal part, it is 1.2 to the power n u of minus of n minus 1. So it is a linear weighted sum of two sequences. One of them is causal, one of them is anti-causal. So what will be the Z transform of the sum and the ROC? And interestingly, we will see what will be the Z transform of the sum when the signal x of n is no longer 0.9 to the power n, but it is 2 to the power n into u of n. Then what is the interesting thing that will happen? So let us go through this example carefully. It will tell us something. So let me take a look. Voila, waiting. Okay. So we can directly use the results, whatever we have derived for the causal sequence and for the anti-causal sequence. So we know that it is z by z minus gamma, where this is gamma to the power n u of n. And similarly here it is z by z minus gamma, So earlier we had minus gamma to the power n u of minus n minus 1. For that it was z by z minus gamma. So now here if it is plus 1.2 to the power n, then you will have a minus sign here. So minus z by z minus it the okay. Okay. So the common region where both x of z and y z converge is this particular region. So wz, the transform of this, can be written as x of z plus yz using the linearity property of z transforms. That comes out as a sum of these two expressions. And you can finally derive it as like this. So the annulus is given like this. So this is our example of a bilateral Z transform of a two-sided signal. So we had earlier derived individually for causal and for anti-causal signals. Now we are looking at the linear sum of both causal and anti-causal sequences. Now what happens if I change x of n from zero point 0.9 to the power n to 2 to the power n u of n? If I do that, then the region of convergence of x of n will go beyond 2. It will be mod z greater than 2. And the ROC of yz is mod z less than 1.2. So there is no intersection. Okay. So there is no intersection. So Rx intersection Ry is a null set. So if that happens, then the Z transform of Wn does not exist. If the ROC doesn't, if the Z transform expression doesn't converge for any value of Z, then the Z transform doesn't exist. Okay, I hope this point is clear. If you're having any doubts, please ask me. So because it was zero point 0.9, the ROC of the causal part will be extending outwards from 0.9. Now suppose this 0.9 becomes 2, then the ROC circle will be somewhere here, outside 1.2, and the ROC of the causal part will be beyond 2, and the ROC of the anti-causal part is extending inward from 1.2. So there is no intersection of those two ROCs. So therefore, you will have no Z transform for W of n. I hope this point is clear for everyone. Okay?
Yes.
Yeah. So let's move on. So similar point here. Now just to summarize this point here. So if you write x of n as a sum of a right-hand sequence and a left-hand sequence, then the Z transform exists only for this particular region. This is an annulus region. If this condition is violated, then the Z transform does not exist. You see the right-hand signal has alpha to the power n, u of n, and the left-hand sequence has beta to the power n, u of minus n minus 1. Only if mod alpha is less than mod beta, a Z transform can be found, and the ROC is an annulus region. So ROC is mod Z greater than mod alpha less than mod beta. But if this particular condition, mod alpha less than mod beta, is violated, that means if mod alpha is greater than mod beta, then the Z transform does not exist. This is a summary of my previous example. Okay. Those who are writing, if you want to write, you can write. I'll wait. Shall I go ahead?
Yes, sir.
Okay. Okay. Same fact covered here. So I'm explaining this fact in detail. So make sure that you understand whatever is going on. So again, this is sum of two causal and anti-causal sequences. So we have the two expressions like this using the bilateral Z transform. So we will have to consider two different cases. In these two cases, first case where alpha mod is greater than mod B, the ROCs will not overlap, and so the Z transform does not exist. For the second case, there is an annulus Z transform or annulus ROC. Okay. Okay. So this is the picture for the first case where mod alpha is greater than mod B. So the causal part has a exponent which is a higher magnitude compared to the anti-causal part. So x of z will not exist for this, and only for this case where mod alpha is less than mod b, you will have an RC. So with diagrams, I'm making it clear that this particular case has to be dealt carefully. You cannot just derive the expression and write something. You'll have to think about the RC. Okay, is this clear?
Yes, sir. Yes, sir.
So let us look at some examples. So here you have two-sided sequence, 1.2 to the power n u of n plus 3 to the power u of n minus 1. So the ROC will exist between these two limits. And similarly here, 0.85 to the power n cos of, this is a cosine signal here, cos 2 pi n by 6. So the right-hand side is a cosine signal. Left-hand side is also a cosine signal. But this is 0.9 to the power n. Here it is 0.85 to the power n. And this part is the anticausal sequence. So if you see here, alpha is 0.85 and here alpha is 0.9. B is 0.9 or beta is 0.9. So alpha mod is less than beta mod or B mod. So therefore you will have an annulus ROC. But for these two cases, there is no ROC because alpha mod is greater than beta mod for these two cases. So the Z transform for these two sequences, it doesn't exist. Okay. What about the Fourier transforms? What about the DTFT? Will the DTFT exist for these two signals? Anyone? Can you see my
No,
cursor?
no, sir.
Yeah, good. Why? Can you explain?
So DTFT is a case when mod of Z value is 1.
Very good. So here the ROC is beyond 1. It is greater than 1.2. Similarly, here the ROC is less than 0.9. So it is less than 1. Okay. So it doesn't include the unit circle. So if the ROC doesn't include the unit circle, then the DTFT doesn't exist. But the Z transform exists. Okay, that's why Z transform is more general form of analysis of a sequence as compared to DTFT. For both these two sequences, the DTFT doesn't exist. And for these two sequences, the Z transform itself doesn't exist. Forget about DTFT. They are tricky things that you should all understand. Okay. Just working out problems is not good enough. You have to have some insight what is going on. Okay. Shall I go ahead? Is it okay for everyone? Have you understood whatever I'm saying?
Yes, sir. Clear, sir.
I'm not hearing any voices. Everybody is quiet, or either they're not listening or they're just keeping quiet. So this is the summary slide of all the ROCs that we have discussed till now. Who is coming so late, Baba? So this is the summary slide. So for a causal sequence, this is finite duration sequence, mind you. So this ROC is the entire Z plane except Z equal to 0. Okay, so n is positive. So xn z to the power minus n. That means it is xn by z to the power n. N is positive. If you put z equal to 0, then that expression goes to infinity. So the ROC will exclude z equal to 0. Similarly, for anti-causal finite duration signal, xn divided by z to the power n. Now n is negative. So it is something like xn into z to the power n. So if z goes to infinity, the expression goes to infinity. So x of z goes to infinity. So therefore, anti-causal finite duration signal will exclude the point infinity. it will include the term z equal to 0. Okay, so these are the two ROCs. The Z transform will converge for all points in the Z plane except infinity and at 0 for these two signals. Now, if it is finite duration two-sided signal, then this is the ROC, the entire Z plane except Z equal to 0 and Z equal to infinity. It is the combination of these two. Okay. Now, for infinite duration signals, it can be a causal sequence, it can be an anti-causal sequence, and it can be a two-sided sequence. So for a causal sequence, we know it is beyond the radius of the circle, and for anti-causal signal, it is inside the circle, and for a two-sided sequence, infinite duration, it is an annulus region. So this is the summary of all types of signals for which the ROC can be calculated in the Z transform. So if you want to make a note, you can make a note of this. So with this, you can visualize various kinds of sequences. Is it okay, everyone?
Yes, 1 second, sir.
Hmm.
Okay, sir.
So with this, we have completed the discussion about like basic signals and their ROCs. So now we'll move to another like sub part of this chapter, which is properties of the Z transform. So we'll look at some of the properties, just like we had taken a look at the properties of DTFT. So here we will also take a look at some properties and the motivation behind using Z transform, why we use Z transform to analyze signals. And so after this, I will cover uh, something about poles and zeros, or how to visualize the system transfer function h of z. So I'll try to give you some idea there, and then we'll move on to inverting Z transform, that is calculating the inverse of Z transform. So if you are given the Z transform expression along with the ROC, how do you get back to x of n? So how do you get back to the time domain? So that we will cover. So let us look at the table. So we have many properties here. So the first one we have already seen, the linearity property. It is simple. The ROC will be the intersection of both the individual signals. Then we have this translation property, just like we had for the DTFT case. So for the DTFT case, it used to be e to the power j omega n naught, isn't it? E to the power minus j omega n naught. So here z is equal to r into e to the power j omega. So you can put this thing here. So you will, if you put r equal to 1, then you will get e to the power minus j omega n naught. If you want to derive the DTFT condition, DTFT property. So the general property from the Z transform is z to the power minus n naught. Okay. Then you have Z domain scaling, and for the particular case of multiplying a sinusoid with x of n. So here you are multiplying a complex exponential in the time domain, a to the power n into x of n. So suppose you multiply a complex sinusoid with x of n, then what happens to the z transform? Okay. So you can derive the corresponding DTFT by fixing z as e to the power r into e to the power j omega. Then you have the time reversal, the upsampling operation, conjugation operation. This is the most important one, the convolution operation. So if you are convolving two sequences in the time domain, that is equivalent to multiplying the z transforms of the individual signals. Okay. Again, here the ROC you note, it is the intersection of the ROC of the individual signals. And then you have the differentiation property in the z domain. So if you have n into x of n, then you have this property. So we will see some examples. Then the differencing and the accumulation properties. Okay. All this can be derived simply. This is very simple. X of z minus z to the power minus 1 z xz, because you are using this property here. Translation. Can you see my cursor? X of n minus n naught. So n naught is equal to 1. So n naught is equal to 1 here. So z to the power minus 1 into xz. So you can directly derive this. And this you can derive by considering that this is a convolution of u of n with x of n. I'll come to that. So if convolution of u of n with x of n, then in the z domain it is a product of the z transform of u of n into z transform of xz. Okay. So that is a trick here. You can imagine this accumulation as the convolution of u of n with x of n. And here there are two more theorems, the initial value theorem and the final value theorem. So initial value theorem is very easy to derive. So x of 0, because you have x of z is equal to summation n equal to minus infinity to plus infinity x of n into z to the power minus n. So if you want to get x of 0, then you just put limit z tends to infinity in x of z. So you will get this term. So it's easy to derive. So we'll look at these properties, and we'll also look at some examples. So this is one part of the chapter, and then we move on to the description of LTI systems, system transfer function or h of z in the z domain, and how to think about it, what happens when you have poles and zeros, how to think about it in the frequency response. So that I will cover a little bit, and then we go into inversion of the z transform. So after inversion of the z transform, mostly I will conclude this chapter. So these are some of the z transform pairs which are generally used. So the impulse, the Kronecker delta has a z transform 1, ROC is all z, UN, that is a causal sequence. So here the exponent is 1. Causal sequence is generally given as alpha to the power n u of n. And anti-causal sequence is minus beta to the power n. Beta is again 1 here. So these two are identical. If you see the expressions, they're identical, but their ROCs are different. Okay? All of you can see my cursor, right? So see their ROCs.
Yes, sir.
So this is the double pole property. Okay, z by z minus 1 whole square. So there is a double pole at 1. Okay, n into un. So this is the derivative property. of Z transform. So you are taking derivative of this guy, minus d by dz xz. You see this, minus z into d by z dz xz and into xn. This is the property you are using. Okay. So this is what you are deriving. Ah. So this is a double pull at 1. So we have already seen this, z by z minus a, or sometimes it is written as 1 by 1 minus a z inverse. Again here it is also 1 by 1 minus a z inverse. And this is the double pole property. Double pole at z equal to a. So the right-sided cosine, the right-sided sine, you can derive all this by using the expression e to the power j omega naught plus e to the power minus j omega naught n divided by 2 for cos omega naught n. And similarly, for sine omega naught n, you can use the formula 1 by 2 j omega naught n minus e to the power minus j omega naught n. By using this, you can derive these two expressions. And these are just general forms of the used two expressions. So these are some Z transform pairs that we should know because we'll be using them in the problems. And each of these Z transform analytical expressions comes with the ROC. So we should have an idea about the ROC. Okay, is it clear? Shall I move ahead? So you can refer to the book and you can take down these formulas. Just I want to hint at what properties are being used to derive this. So again, similarly, you have this slide. So this one you be a little careful. Here you see this is a to the power mod alpha to the power mod of n. Okay. So I want all of you to look at this particular example. Can you all see this? Shall I zoom it? Can you now see my cursor?
Yes, sir.
Yes, sir.
This one you try to work it out yourself. This is alpha to the power mod of n. This is a two-sided secant. Okay. And you have to worry about the magnitude of alpha. This magnitude of alpha can be less than 1, it can be greater than 1. So all of you take it as an assignment to derive this and look at the value of alpha, magnitude of alpha, and see what will happen when it is greater than 0, less than 1, and if it is greater than 0, greater than 1, what happens? Okay, there is a repetition of the previous slide. Only one property I could find. So I'm just explaining one by one the properties with little detail. So the first property, but whenever we talk about these properties, we have to be worried about the ROCs. So the ROC of the first part is ROCG, and the ROC of H of n is ROC subscript H. Then here, when you have a sum of two different sequences H of n and G of n, a linear sum, then the ROC is the intersection of the individual ROCs. And for this shifting case, the ROC is identical to the ROC of G of n, except Z of 0 or Z equal to 0 or Z tends to infinity because of this particular term, n naught. Because we are multiplying Z to the power minus n naught. So these 2 points can cause a problem. So change of scale in Z, or you're multiplying complex exponential in the time domain. So ROC is equal to mod of alpha into ROC of G. So you are dilating, either contracting or expanding the ROC of the original signal G of n. This is a nice property. You can look at some problems with respect to this particular property. So time reversal, and the ROC becomes the inverse of the ROC of the previous signal G of n. So ROC of G of minus n, or the transform of G of minus n, will be the inverse of the ROC of G of n. Okay. Conjugation property, Z domain differentiation property. This is important because here you see minus is coming here, so there is no minus here. If it is just n into G of n, then there will be a minus Z sign here. Minus Z into d by dz of G of Z. Okay. So I'm moving to the next slide. the convolution expression. Again, here the ROC is the intersection of the ROCs of the individual signals. And the first backward difference, this is 1 minus Z inverse. You can derive this very easily. And the accumulator, I have already said that it is U of n convolved with G of n, this particular expression. That is why you get this, the initial value theorem and the final value theorem. Okay, fine. So there's a small catch here for the Z transform properties. We can just skip this for the time being and we'll come to it when you're working out problems. Okay, so we'll have examples to illustrate the properties of the Z transform. So I have 5 minutes now, so I'm just not getting into this right now. Tomorrow we have a 2-hour class from 6 o'clock. So we will start looking at some of the examples and we'll have more detailed discussions. So you can all refer to the textbook and read and come so we can look at some examples, you can understand better. And I will be sending out the Google folder link to share the Google folder with all of you. So because we'll have the class test on Thursday, so I'm going to send out mails to everyone sharing a folder and let me know whether you are able to get the access to that folder or not. Once I send the link to all of you. Is it clear to everyone?
Yes, sir.
Yeah. So I'll be doing that today. And once you click that link, you will get access to Google folder. And on that day, I will expect that at the end of the class, you will take the pictures of whatever you have worked out and you will upload as a PDF file into that Google folder. So Z transform is included up to tomorrow evening, whatever I teach, that is inside the syllabus of the of the class test. Okay, if you have any doubts, you can ask me. Okay.